Hello everybody, welcome to the second lesson of Discrete Mathematics Circuit Logic. Now before we begin, we will first see a lecture and then we will build a circuit, which we shall see this on the screen here by getting as close as absolutely possible to it. Yep. There are three parts to logic circuits: the logic gates, the circuits themselves, and then truth tables, which you've already learned a bit about, but they help to kind of understand how every single input leads to certain outputs. Now, let's go ahead and reveal the first part of our logic gates part is, well, the logic gates themselves, what they look like, what they do. The NOT gate is basically they invert the polarity of they invert the truth value of the input. Ignore these letters here. I just stole them from Wikipedia because I don't want to just hand draw them for the hell of it. But the NOT gate say if the input is true, then it will turn it false, and if the input is false, then it becomes true. The AND gate, of course, does the same thing as the AND logic operator. If both inputs are true, then the output will be true. Otherwise, it's going to be false. The OR gate is basically if any of the inputs are true, then the output's true. Otherwise, if both the inputs are false, then output false. Otherwise, it's basically true. And of course, there's the NAND gate and the NOR gate, which is basically NAND and OR gate with the circle in front of it. I actually learned this while looking at Wikipedia to steal the graphics, but this is a buffer. The symbol for buffer, if you remove the circle, that's what the symbol means. As for what the buffer means, it basically means that the thingy is, it's kind of slows it down, isolates it from the thing. You don't have to know about it, but if you want to read up about it, Wikipedia is a good friend. And if you're wondering what XOR is about, there's also this symbol here. And if you want to know what negated XOR gate looks like, all you have to do is just put a circle in front of it, per usual. And let's go ahead and reveal the second part of our ignore the extra cut there. The second part is the usual circuit diagram. As you can see here, we have three inputs, which we have assigned these variables here. And given any of the truth values for this, for P and Q, we have an stretched out OR gate here, which is P or Q here. And then we negate that with a NOT gate here, which is P or Q, not P or Q, in parentheses there. And then we also have R here, a third variable, which makes things very complex, kind of, because it kind of becomes from like when we are having to deal with like four possible outcomes, true, 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 false, false, true, false, false. We now have, well, we'll get to that. So, we have not R here, and then we combine these outputs together to make not P or Q or not R. And what are the outputs for all this? Well, here's a convoluted truth table for all this. We have true, 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 false, true, false, true, true, false, 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 true, 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 false, false, true, false, 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 true, and false, false, false. And then P or Q, we have true, 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 all that, and then the bottom two are false because those are the only two values that are false. And a lot of the results are kind of duplicated, like these two are effectively the same here. Why don't we go ahead and actually show this. Let's go ahead and visualize how similar these are. We have the double true here, a double true false here, and we have the double false double true, and then we have all falses here. And they all kind of go into this area here. And of course, that's just gonna be what happens, but you don't have to worry about filling out truth table like this too much. All you really should care about are the circuits. And then, you know, we just negate this, so all we have to do is just kind of move this huge thing, and then this turns into false, and then all this false becomes true. And then for R, well, it's as simple as just flipping all of this to this, which is a bit of a repeat since it's all true, false. You can just duplicate that all over again. But then we have this little thing here, which then we have to take all of these and then figure out, or actually just these two. We're not worrying about this anymore. We're just worried about these two, because these two are basically the only things that we are operating on. Because this is inputted into this OR gate here, and this R here is getting inputted into this OR gate here. And so this compound statement here, you know, we just, anything that's true within these two columns here, you know, this is true, this is true, this is true, and all these are also true. Now that we know that given a certain combination of things, we know that basically if there's anything that's very determinant on what the circuit is going to output, we can basically say that it's whatever not R is going to be, because that's what most of the outputs are going to become. If R is true, then the function's likely going to be true, because all this is false, right? And it's going to be not R that's really dependent on it. But the only exception is when P or Q happen to be P or Q happen to be both false. P and Q happen to be false, because then it gets turned into a true one after they both get negated. And then because they're both true, regardless of what R is going to be, it's always going to be true here. And now that we have this, you can basically kind of, if you have the basic instinct, if you've played a fair bit of logic games here and there, you could probably construct your own logic circuits as well and try and get a certain output. And one of the more basic logic circuits that you can construct is by building a simple password machine, where basically, given a set of various variables here, or set inputs, really, basically, whatever buttons you have to push or levers you have to keep down, these things here, you'll always get a false result except for the right combination of true and false lever, you know, whichever levers are being pulled down, whichever truth values are true or false. And so, if you can construct your own password circuit, then, you know, it's one of those more simple ones, and I'll go ahead and leave that up to my future self to teach you how to do that. Thank you all so much for watching, and I hope you've enjoyed, and if you like this video, please like and subscribe, because I'm going to ask you again after I'm done building this password machine in Minecraft. Now that we're done watching the lecture, let's go ahead and start building logic gates, and making a simple project, which is a simple password unlocking mechanism. And let's go ahead and actually show you how to make these logic gates. This is a NOT gate, which is a simple basic, if the input is on, if the input is 1 or whatever, then the output is false. It just simply reverses the polarity. Not that hard. And here I have an OR gate. If any of the inputs are on, or both, does not really matter, then the output will be on. And here's a simple AND gate, where if it requires both of the inputs, so that way this turns on, and it is off otherwise. Now, the thing about Redstone is that you can actually compact this a little bit. And this is also kind of indicative of like the operations, the logic operations, as you can see here. Basically, here we have a bunch of an input with 3 inputs here, all in one big OR gate, because ORs just check if any one of these is true, then it will output a true. It does not matter how many you put into conjunction, like say like this, and then do it like this. It's basically the same thing as just connecting them back here anyway. Like they are all the same regardless. They are all the same. It does not matter which one is on, the OR gate simply does what it does. And for an AND gate, if any one of these inputs are not on, then the output will also not be on. So you can connect them all like this, and then have this happening here, and then we can basically have that. Now, how do we go ahead and build a password generator, or not generator, but like we want this to be our password, a simple asymmetrical kind of, if it's laid out like this, this last one isn't going to be one of our wanted inputs, right? You want to connect all of these up, so that way when these are all connected right here, we want to make sure that all of these turn off. And the output here is true. Well, let's not fry our stuff real quickly. But the thing is that with this one here, we have two inputs here that we want to make sure that if these are on at any capacity, then we want to make sure that we want to check for that too. So let's go ahead and check if any one of these other inputs that we don't want are on. And we can do that by turning it into an OR gate. As you can see, by having this. So currently we have, that's currently on, but if any of these are on, that turns on, that turns on, and that turns on. And if any one of these are turned on, that stays on. So we've now checked to see if any one of the wrong inputs are turned on or not. And just to double check if the AND gate is working or not, yep, as you can see here, that light turns off. This doesn't turn it on. This doesn't turn it on. That doesn't turn the lantern on. These two combinations don't. This doesn't. This doesn't. All three need to be on. Does not matter which one. All of these have to be on. Doesn't matter which one is off. Or rather, it does matter if one of them is even off. It's just that it doesn't matter which one specifically is off. So long as one is off, that output will be 0. And if any one of these is 1, then we have that output here. And now, basically, now we just want to connect our outputs. And we can just simply bring that down real quickly. We want to bring this output down. And so we have this lantern here, but we don't really want to worry about that yet. Let's just go ahead actually and just extend that real quickly. Then we do a little bit of tomfoolery. And so we want to turn this into an AND gate, basically. Such that if any of these are on, then that gets turned off. Rather, since all these inputs are off, we want to make sure that we basically want to negate this first, actually, by doing this. And then we bring an input up here. Oh, whoops. Something fried. Oh. That happened. Okay. I see what happened. And so now that we have all this on, we check if that's on, and then we want to make sure that this output here is also on. And once we have that, this goes in. And let's go ahead and double check again just to make sure that we did all the circuitry right. So, P. That does not turn it on. And having the wrong input turn on also doesn't turn on the gate, which you can see here, right there. P does not turn it on. You can see it right there. Q, nope. And we can try all the infinite combinations, all 200 combinations there, but it only turns on when the specified inputs turn on. As you can see, the gate is opened. And if we turn on one of these, oh, look at that, that's off. Simple as that. Yep, pretty much as simple as that. We have now successfully built a simple password locked gate. And once we put in the password, and that opens, and wrong input keeps it closed, let's go ahead and enter it and see what's behind the door I've built.